Hi, everybody. It's Sunday night, 9:30 Eastern, 6:30 here in California, and we've got people from all over today. So it's something 30 someplace. So welcome back to the Astro Imaging channel. Tonight, we're going to take you on a little adventure. There are two adventures that we like to take people on around here. Um, and one of them is workshops, which is what we're going to do tonight. And so let me show you about workshops. Oops, I want to go to this one. It's Sunday night, 9:30 Eastern, 6:30 here. This is the TAIC workshop that we're doing here. And as you can see, when somebody, we provide data for people. The current workshop is Terry's. Robeson has given us the Tarantula Nebula from down in Australia. And you had until March 13th to go ahead and get the zip file. And by the way, you can still get this zip file. And then you can submit a finished image here. And several people did present those images. And Rory, who handles this part of the Astro Imaging channel, put them all together. And we're going to show you how they process their data. The reason I've got this screen up today, and it's the astroimagingchannel.org, TAIC workshop. The workshop, we've had these programs here in the past. We've had several people, Eric, me, Steve Miller. They've presented workshops, and you can still go back and get this data and submit them. Well, you can't submit them anymore, but you can work on them and use them. It's all, generally speaking, pretty good data. Particularly Eric's and Terry's data has been pretty good data. So you can work on these and practice your processing skills. So we're going to be on YouTube tonight. As you can see, there's a room over here for people to ask questions. If you have any questions about what the presenters are talking about, they'll each be here presenting how they process the data. You can ask it over in this area, and we'll try to get back to you. The other programs that we have are TAIC shots, and these are user shots of this particular topics. Now, this one that we're doing right now is called the solar system, and you have until, what's that, Friday, April 3rd, to submit your entries into the TAIC user shots programs. And then Arno, who's one of our friends on the Astro Imaging channel, will put them together into a program like these here. These are videos with music, and it includes a lot of your shots that you've already put in. Now, we're running a little slow on this. Okay, guys, we still don't have enough shots for the TAIC user shots. So please, if you've got some solar system shots of any kind, comets, the planets, moons of the planets, anything that's happening, or the sun in the solar system, please send them in to us. But tonight, as I said, we're going to be talking about the workshops, and the guy who's in charge of the workshops is Rory. And Rory, you've been working with these guys for a while now. Could you go ahead and tell everybody what you've been doing and start the show for the night?
Yeah, can you hear me okay?
Yeah, you're good.
All right, I'm going to share my screen here. One second here. I should have practiced before the show. I have some system preferences I now need to deal with. Give me a second here. Sorry about that, you guys.
While we let Rory fix his problem, Terry, why don't you tell us about how you acquired this data? Why don't you tell us a little bit about your setup and when you acquired it and how you acquired it?
Okay. I run an autonomous robotic telescope in Australia.
Turn your camera on, buddy.
Oh, sorry. Sorry about that. Hi. I gave a show several years ago on the Astro Imaging channel about batteries and observatories. I run a robotic telescope system out in Australia. It's located a couple of 100 kilometers from here. The last time I visited was probably 2 years ago, so it hasn't had any carbon-based units turn up and poke and prod at it. Just spiders and other creatures. That's about it. I am trying to get out there to clear out all the cobwebs in the end of the OTA. But I'll show you a picture of what it looks like. Just one sec. I'll just share screen here. And present now. Okay, so what I'm running is a scope dome, 3-meter dome.
It's not up.
It's not up yet. Okay.
There you go.
That's okay. That's what the telescope looks like. The dome. So it's a scope dome that comes from Poland. It's a 3-meter dome. It's sitting on top of a composite deck and thin metal superstructure. The reason I chose that is that it casts a shadow on the ground. So when it turns to imaging time, that part of the ground is already quite cool. If it was sitting on a big concrete slab, I would have a lot of issues with equalization. So as soon as the sun sets, I'm ready to go. There's no tube currents. There's no eddies coming up through the dome whatsoever. Like I said earlier, it's completely autonomous. There are no communications out there. There's no power out there. So I do everything through the mobile phone network. It's basically an industrial modem. This is my communication shafts. These are antennas to point to very far away towers, which I just barely get a signal. I've got wind speed. I've got multiple sky cameras, multiple devices here for measuring whether the conditions are okay, if I should close the dome, because there's nobody out there. And it has to make all of its decisions all by itself. The array out there is a 3.7 kilowatt array. That goes back into a battery hut. That's the control board there. So I can isolate each of the strings. This is the modem up on the top here. There are relays that I can toggle stuff by sending it text messages through the phone network. I can go power off, AC power on, AC power off. It's got three-phase power, 240 volts out there, as well as a 48 volt. I got an 11 kilowatt battery system out there. The battery system are made up of lead carbon batteries. They got about a 20-year chemistry life. I chose that technology because it requires no active cooling. I didn't want anything that required a mechanical fan that could fail and then have a thermal runaway. So these are completely passive. There's lots of cables, redundant cables running underground to the dome because, funky things can happen. I have another all-sky camera here. This is one of 3 I have out there, where I can look at the sky. The acquisition software, my stuff is all pretty old. The cameras for the data tonight, it's about a 12-year-old camera, so it's pretty old. The software I'm using is very old. It's an Arcos, so this software is written for the Windows 3.1 era. So getting it to work now is a little bit challenging, but it does work. The telescope itself is a 10-inch RC, 2300 millimeters focal length. It's running on top of an astrophysics mount. I've built all the control systems for the dome as well, so they're all independent of a main computer. So everything has been designed so if there's a fault, it rehomes to zero, starts from scratch. This is what the modem looks up close up. I zoom up on that. So there are a set of relays. So when I send it text messages, I can toggle relays on and off inside the dome. Because if I get into a situation where I have, say, the switch needs to be repowered or cycled, I can actually cycle that just by setting it a text message. There's nobody out there to help it along. Tonight's data, this is a all-sky camera video from one of the cameras. This is taken around the vintage of when this data was taken. This was taken in 2018. This is the southern skies here. That's the dome working in the background. Zipping around, and as it gets to morning, you can see the large and small magnetic clouds rising there, which is what our presenters will be presenting tonight, and how they tackled this really old, noisy data. I'm going to hand it over to Tim or Alex. Alex, over to you.
Actually, why don't we go back to Rory? Rory, you good to go?
Rory, yes.
Yeah. Let me see if I could present now. If you want to stop sharing, Terry, and then I'll give it another try. If not, then I'll just have to wing it from here. Yeah, it's still giving me some run around here. So I'll tell you what, I'm just going to try to wing it from here. And basically everything I was going to say, you guys touched on anyways. So I'm just going to open it up with Jason Dane. I got Jason Dane, John Richards, and David Biggs, who presented their image through the Astro Imaging Channel TAIC workshop. So thank you guys very much for accepting to present tonight. And I'll hand it over to Jason first.
All right. Thanks, Rory. I will try and share my screen. I know Google has had some problems this week with screen sharing. I've struggled with it a bit at work, so it's probably not you. So, all right. So I'll start off my presentation. As Rory said, this is the my version of the Tarantula Nebula processing. I'm Jason Dane. I'm based out of Halifax, Nova Scotia, Canada, on the eastern seaboard. 1 hour later than Eastern time in Atlantic time. So it's 10:42 here. So I'll give you just a brief introduction about myself. So like I said, I'm based in Halifax, mostly backyard astrophotography. I do take my gear out to various dark sky sites around here. I'm very lucky to have Bortle 2, 45-minute drive from home. And I can get to Bortle 1 in about an hour and a half if I want to go that far. I currently run 3 rigs. I have a Skywatcher Esprit with a ZWO ASI 2600 camera with filter wheel and filters on an EQ6R Pro mount. I also have an Explore Scientific 127 carbon fiber 294 camera with another EQ6R Pro mount. And then I've just recently sort of built this third wide field rig with a Samyang 135 millimeter camera lens with a 294 that I kind of swap back and forth with the 127. And I was kind of switching it with my other EQ6. But I broke down and got myself a smaller mount to run it so that it can be dedicated if there's enough targets to shoot, which unfortunately this time of year there isn't. I use an ASI Air to control all my stuff. I have 3 of them. I use autofocusers, filter wheels, and Pegasus power boxes for hardware control. I've been at this a little over 2 years. I spent a fair bit of time when I first started working with Ron Brescher and the Masters of PixInsight to sort of get a kickstart into PixInsight, which is what I use pretty much exclusively. And I just wanted to thank Terry for sharing the data and AIC for having me present. This is my first go at one of these things, so this is interesting. So, and if you want, you can find me on Instagram at Dane Jason. So I'll get into, so my process is kind of pretty linear. I think, not in the imagery sense, but I sort of approach things very sort of systematically. So I deal with the linear processing of my color image, the linear processing of the luminance, and then I bring them all together and do the nonlinear processing. So I sort of have 3 streams. and I typically process all my data that way. So I wanted to just give you an example or sort of an overview of how I tackled this. So I started off by doing an RGB combination, and I'll walk you through the sort of the history of the image in PixInsight after. I did a background extraction to get everything nice and even, which the data was really clean, so that there wasn't really much of a gradient. Then I used I think it's actually the NB RGB combination script, not NRGB. So basically, I combined the broadband and narrowband images together to create my color master. Color calibrated it based on a small preview of sky, which was exceedingly hard to find in this image. It's quite unbelievable how much stuff is going on in this image. There's nothing like this in the Northern Hemisphere, I don't think. So it was quite a challenge to find something appropriate for background. MLT to do denoise, which is what multi-scale linear transformation. I use, before stretching, I use the repair HSV separation script just to basically fix any blown out cores on the stars. Even though there was short exposure color data provided, I still wanted just to sort of have a good sense of how things looked before I decided to use that later in the process. Because sometimes I don't have that data with my own. So I tried it without it first, but found I still wanted to save some of the brighter star cores later. And then I did a mask stretch to about 0.125 background. And that sort of ended as my color master. So that was kind of where I got to with my color data, or with the color data, I should say. It's not mine. So then nonlinear. So for the luminance data, I did a HDR composition because there was both longer subs and short exposure subs for the luminance data. Although I didn't find when the HDR composition output the map of where it replaced the short exposures, there was just a handful of star cores that it actually pulled in. So it was useful. I thought it would actually be quite a bit more useful in terms of this area here, but it didn't really find anything to replace. So it's just a standard, if I get bright stars, then I will shoot short subs as well, just to rescue the star cores. Then I did just, the standard preparation for deconvolution. So I created a local de-ringing support image, point spread function image, and a deconvolution mask. I then ran deconvolution about 30 iterations, did my MLT denoise, and then stretched to about 0.1 or so background, and then I had my luminance master. So I sort of processed my RGB until I had my master, and then I processed my luminance, or the luminance, until I got my luminance master. And then basically I brought everything together. So I did, it actually should be LRGB combination, not RGB combination. My apologies. Oh, I'm sorry. Back up. I got out of sync. So at this point, I decided that I needed I wanted the short exposure color. So I did a similar process, but in this case, I basically extracted the luminance from the color data, stretched it, saturated it, and basically came up with my, my star mask for the short exposure color, which I blended in later. So basically once I converted it, I had everything in my color and my luminance were converted to linear. So then I did my LRGB combination to get everything together. I did the TGV denoise with a inverted luminance mask that was basically clipping the shadows. And then I usually find that after TGV denoise, the histogram has a little bit of slack on the left, so I brought that in. Then I did HDR multi-scale transformation. So I created a clone of the image. I ran HDR multi-scale, and then I tried blending it in at a few different ratios with my master just to see how things looked, and I found that a 3:2 combination of the regular image to the HDR image worked well. Did local histogram equalization 2 different times with different settings. Ran the dark structure enhanced script. And then I went into mask making mode, which is what I usually do at this point. So I created various masks to do different things. So I created a sort of a starless mask of the hydrogen, the oxygen, and then the color, so that I could treat the nebulosity and the stars separately. And then I basically did a bunch of hue and saturation adjustments to taste. I wasn't really looking at other people's versions of the image. I kind of got it to the way I liked it. Then I blended in the short exposure stars, exported it to a JPEG, and that's kind of where I left it. Can you still see my screen? Yeah.
You're still on the screen.
Yes. Okay. So I basically I always work in projects. I still hear Ron's voice in the back of my head from my early days, is always save your work in a project in case you have to go back. You don't have to, you don't have to try and figure out where you were. Although now with the new version of PixInsight, the processing history is stored in the image, even though you don't have a project. So it's, you don't keep all the masks without the project, but this way, I have everything that I did, which there was a lot of masks and a lot of different steps. So I will show you kind of the evolution of the image. So I'm starting off with the result of the NB RGB combination script. This is kind of where I came out with. The RGB data looked really good to start with, but I wanted to kind of boost some of that narrowband data. So this is what it looked like, and then I'll just kind of skip ahead. So let's see here. Change the name. The going through the different processes. Found my background. Oops, now I'm linear. So hang on. Here, let's go back a few steps. So this was the probably the denoise. And then I got to the point where, let's see, where am I at here in my history? Oh yes, so I did my curves. And then I just worked through, and then I got to the stars. I inverted the image because I found there was some magenta that I didn't really like. So I inverted that, did SCNR on the inverted image to get rid of the magenta. So you can see here, you can see, like, for example, here, this is really pixel peeping, which I tend to do a lot of just because I'm a perfectionist. So it's not really the something that most people would notice, but I do. So, running the SCNR on the inverted got rid of that magenta, which was good. And I tweaked things a bunch of different times with different masks and trying to isolate different things. One thing I should say that when I combined the luminance, I found that I kind of lost some of the oxygen kind of in this area compared to some of the other images that I've seen of this target. And I didn't really dig into the why. I didn't really want to fake it to make it brighter, but I really have to go back and spend some time to kind of dig into this. I did want to show quickly one kind of just an example of where no, I just need to find one of these masks. Hang on. So that's a starless mask. Yeah, so here's an example of a mask that I use this kind of technique a fair bit. So I will run either StarNet or Star Exterminator on a copy of the luminance data to basically isolate the stars. And and not basically get some weird, artifacts from the histogram equalization or the saturation. So this way I can kind of work with, the image without the stars, saturation and curves. There's a bunch of people on the astrophotography world that kind of start off by going starless and then working that way. I've tried that. I don't really like it, but I see a recent video from Ron about doing that on YouTube, so I may have a look at that and may change my mind. But I really find this works well for me, because I can see the image kind of the way it's going to end up and not have to worry about making it look natural by adding the stars in later. It's kind of a philosophy thing, I guess. It's just the way I've kind of learned and evolved my technique. So I use this technique a fair bit once I get down to the linear stage. So I'll just pop open the luminance. So here's the sort of the result of the HDR composition. And then I ran my deconvolution. I'll just go back here. One of the things that I found that was really tricky on this image was, when I'm doing deconvolution, and again, I really zoomed in a lot, but the sort of the technique is to try and not overdo it. So you can see the before and the after. You really bring in a lot more contrast in some of these sort of areas here. I may have kind of overdone it a bit, I guess, in my, I was kind of creating these wormy areas as opposed to the kind of the knots that I should have been aiming for, but I kind of like the result, so I didn't get too bothered by it. And then I ended up with my stretched version after a few different iterations to get where I wanted it to go. So, and then combined that and went through my linear. So I think that kind of takes up the time that I had or needed. I guess we can open it up for any questions that anybody might have.
Jason, do you have a nice large JPEG where we can see the whole thing on the screen? Final image?
Yep, I do. Hang on a second. I'll just open it up.
Have you published it yet?
You mean like shared the data with anybody else?
Or published it on AstroBin or your own site?
No, I was actually going to ask about that. I wasn't sure if we were permitted to do that. So, I didn't want to share the data without permission. So,
Jason, go for it. Just let people know where it came from. You're free to do it. Yeah.
Oh, absolutely. Yeah. No, I'd be happy to share it. It's awesome data. It was really fun to work with. Some of these Southern Hemisphere targets make me really jealous.
So I take it from your presentation that all of your processing was done on PixInsight.
Yes, I was taught to uninstall Photoshop from my computer once I got into the astrophotography world.
Remember, they're tools. It's not religion. They're all tools.
No, I understand. It's a joke. It's a joke.
We understand the joke.
I've been at bird photography and wildlife photography for probably about 6 or 7 years now, and I've done a lot of Milky Way stuff, so I'm quite an adept Photoshop user. But I measure my success of an astro image with, can I do everything I want to do in Photoshop or in PixInsight? And the better I get at PixInsight, the less and less I find the need to open up Photoshop for this kind of stuff. So no Photoshop touch this one.
I find most targets in the LMC to be quite challenging. Personally, I've done a few of them, and they're very deceiving. And this one here looks to be very bright, but it's not really bright. The values are all very similar values, and it makes it quite challenging to get your head around that. And I do like your approach where you're not relying on other versions, which makes your final result closer to the original, I believe. It's a good technique.
And before we go on, Matthew Holovinsky wants to know, does that come in a poster size? I think he's trying to say, hey, that looks wonderful. I'd love to have it hanging on my wall. And it is a beautiful piece of work there, Jason.
Yeah.
Rory, how's it working over there?
Working good over here. Jason,
You,
thank you very much for sharing that great work. I've actually found Jason on Instagram. I posted a TAC workshop kind of recruitment image, and Jason responded, and really happy to have you tonight. Thank you. Thanks again for sharing.
Yeah, great. You're welcome. It was lots of fun, and hope to do one of these again. It's always fun to process, other people's data, that especially data of this quality. It was a bit mind blowing to sort of see this kind of data and be able to have the privilege to work with it. So I'm very appreciative.
and we have a question from Conrad. He wants to know how we got the image from the Southern Hemisphere. And the answer to that is that the idea behind the TAIC workshops is that we get data from various places. In this case, Terry Robeson, who is in Australia, and he makes it available, and everybody can use it. The process, and that's the challenge, is to get everybody to process the same bit of data, and that's what's happening there. Okay, Rory, where are we going next?
All right, next presenter is John Richards. John, you out there?
I am trying to be. Hang on, my camera has decided not to cooperate. Let me quickly reboot it.
If it's giving you problems, just let me know, and we can go with David first. Oh, there you go. There you go.
Nope, I'm back on. All right. My name is John Richards, and I'm located in Warner Robins, Georgia, which is about 120 miles south of Atlanta. I've been doing astrophotography for about 4 or 5 years. I do most of it in my backyard in Warner Robins. It's about a Bortle 5. So could be better, but could be a lot worse. I also belong to the Middle Georgia Astronomical Society, which has a dark site about 20 miles from where I live. And so occasionally I go out there and do some imaging. My main imaging rig in the backyard is a Stellar View 102 millimeter refractor on a GEM 45, and I'm using an ASI 294 Pro as well as the MC Pro. Alternate them in and out depending on what I'm imaging, and generally use a laptop for the main imaging rig with astrophotography tool as my acquisition software, and of course PhD2. My portable rig is a CEM 25P mount with an Astrotech 72 ED2, and I usually put the ASI 183 MC Pro on that for imaging, and control everything with the very original ASI Air version 1. I do publish my images on both AstroSpin and Telescopius if you're interested. So let me go ahead and share my screen. Okay, can you see my screen okay?
Yeah, looks good.
Okay. So I process this in PixInsight. I do also use AstroPixel Processor occasionally, but I did not this time. And if you're curious what the little symbol in the top left is, that's the logo for the Middle Georgia Astronomical Society. I borrowed their template to create this presentation. So just some notes on how I processed this. I created an LRGB HOO image, and I did not use the sulfur data or the luminance data that was taken with 60-second subs. The data, as been mentioned, was really clean, so I didn't even bother to do a background extraction of any type. So I kind of went through 7 basic processes, and I have to kind of explain. I did some experimenting as I did this data, and I processed it fairly quickly. And like I say, I did some experimentation. I probably broke a few astrophotography processing rules. So I may go to astrophotography prison. I don't know. But anyway, let me go ahead and go through what I did quickly, and then I'll go through each step. So I first created an LRGB image, and then added the hydrogen and oxygen data to the LRGB image using, again, the narrowband RGB combination script in the utility tab. I then removed the stars from that image. And then I created another RGB image from the 30-second data, all those subs that were taken. There were 30 for each color, 30 seconds apiece. And from that image, I created a star mask, an RGB star mask. I then processed the first image, the LRGB HOO image, to enhance it and saturate color and that sort of thing. And then I added those stars from the second image to the first image to create the final image. So to create the LRGB image, I did make a lot of use of the easy processing script. That's not something that normally comes with PixInsight. If you're not familiar with it, you can Google Easy Processing Suite, and it will lead you to a website that will allow you to download it and install it in PixInsight. But it allows you to do some of the tasks fairly quickly, maybe not as precisely as you might if you were doing the individual processes, but it's a shortcut, and so I used a few shortcuts. So anyway, the first thing I did was run the Easy Denoise script on the RG and B and luminance images, the main images. And then on the luminance image, I ran Easy Decon, which is the deconvolution. And then I stretched all of those images, the luminance, the red, the green, and the blue. And so they became nonlinear. So here's where I broke the rules a little bit. I used photometric color calibration on nonlinear images. Now, normally, of course, you use color calibration on a linear image. And normally, I have found that the photo color calibration does not even work on nonlinear images. It will often produce an error. However, in this case, it didn't. It did calibrate, and so I went with it. One thing I will mention is that in order to fill in the data in the PCC process, you needed to know the focal length, the pixel size, as well as the acquisition data in terms of the date and the right ascension and declination. And the right ascension and declination data and the date came from the image itself and the FITS header. But I did get the focal length off the notes that came with the package that we downloaded with all of the images in it. And the pixel size is 9 microns, and that wasn't specifically given in those notes, but the camera was, which was an S-Big model. And so I looked that up, and it indicated the pixel size was 9 microns. And so I put all that in there and ran PCC, and it worked. So that's how I calibrated the data. Again, that's that's a rule I broke, but I was kind of playing with the data and experimenting, and it worked. So then I started working on the hydrogen and oxygen data, and I ran easy denoise on both those images. Again, that's part of that easy processing suite. And then stretched both the hydrogen alpha and the oxygen data using, again, easy stretch. And then I added the hydrogen and oxygen data using, again, that same script that was used earlier, the narrowband RGB combination script. Notice, since the data was non-linear, you also have to check that non-linear box. Okay, so at this point, I went ahead and removed the stars, and I used StarNet 2. Now, StarNet comes with PixInsight, but there is a second version that has come out called StarNet 2. And if you weren't aware of it or haven't used it yet, you can download it and install it in PixInsight. And if you want to know how, you can go to YouTube and the site for Visible Dark, which is Sean Nielsen, and he has a video there on how to use it, or where to find it, and how to install it in PixInsight. So anyway, I removed the stars with StarNet 2 and basically discarded them. So then I started working on the red, green, and blue images that were done with 30-second subs. There were 30 of each of those that created each one of those images. And again, I stretched them and then used the LRGB combination process to create an RGB image with that data. And here I'm only interested in the stars. I threw the rest of the data away. And once again, I broke the rules and used PCC on a non-linear image to calibrate it, again, using all that same data to fill in focal length and pixel size. And then I used StarNet 2 again, but this time to actually create the star mask. And that's what I wanted to keep out of that image, was the stars. I then ran the easy HDR script. This is processing now the first image, again, the LRGB HOO image. And I did a light processing on it. I ran the easy HDR script to enhance the details a little bit. And then ran curves transformation process, again looking to brighten it and to bring out the colors to saturation. Didn't really do much else in terms of color with that image. I also ran the dark structure enhance script that's found in PixInsight. And then finally, I used Pixel Math and combined that star mask I created earlier to the LRGB HOO image. And then I ran, once again, going back to the easy processing suite, I ran the easy star reduction script to reduce the size of the stars on the image. And that was pretty much it. So I did it relatively quickly, did not go quite through the detail of the previous presenter, but I did have fun, processing the image and did a little experimenting. So it was fun. So that's pretty much all I got. So if there's any questions, I'm ready to answer them.
Thank you very much, John. That was interesting. It's interesting how you come with the different interpretation than did Jason before you, and that. Rory, where are we?
Yeah, thanks, John, for sharing. That was one of the coolest parts about this image, is there was so much data that Terry posted. Every single person who submitted had a completely different image. So thanks for sharing yours. I thought that was pretty unique. And, you know, like I said, there's just so many different images to choose from and color patterns. So very unique pattern on this one. Thanks, John.
Okay, thank you.
All right, next up we have David Biggs.
Okay, let me share. Hopefully everyone can hear me.
Yeah, we can hear you.
You got to stop shaving. You got to stop sharing, John. Now David Biggs is presenting.
Okay. Hi everyone.
We're good. We're good, David. Go ahead.
Good. Okay. Hi everyone. I'm David. I'm from just outside Sacramento, California. I started in astrophotography only a couple of years ago, and I managed to get my next dome finished right before COVID started. So that was and it's not a solar powered dome. It just happens to be that the solar panels are in the part of the property that have like the best view of the sky, and they also have power to them. So I was able to run a little bit of wire directly from the power that goes to the house, put my pad there, and then voila, I have my dome sitting right there. And I also have a next dome that's on I built a 1-inch riser on my next dome, sorry, a 1-foot riser, and that makes it much easier to get in and out of. So I think all domes should be like 1 foot higher than they actually come. And I'm in Loomis, which is a sort of a semi-rural part of the state. It's a border 5, but my east view is looking out over Folsom Lake, which is actually pretty looks pretty good. So I see a lot. I'm quite impressed by the number of stars I actually see. I also have a stellar view. I have a Raptor, just a 90mm refractor, and probably the number one reason I have a stellar view is because their factory is 10 miles from where I live. So I was able to go there and pick it up directly from the factory, and then I assumed if I was ever going to have a problem, it would be easy enough. So that's why I have a stellar view. And that's not where I have a next dome. The next dome came from Canada, which was always fun, but that's so yeah, I have a fully automated system. I run it all from the house. I have a great, everyone says the mount is the most important part of your system. I have a great Polaris mount that I bought for $300 off Craigslist before I really knew what I was doing. I have stripped that down. I've re-greased it. I have pulled out, took any motors off, put on an on-step system with an custom designed autofocuser, and that has actually been running pretty well. The software uses ECOS. I have an ASI 1600mm Pro on the back with the guide scope and filter wheels. And I just bought myself for Christmas chroma filters, which was, I think, cost more than my scope. And then everything runs also from a web power switch, which is very useful because I can remotely turn things on and off from inside the house if I ever have a problem. So my presentation will be fractionally different. I have never touched PixInsight in my life. In fact, I've actually written my own software. That's partly because I'm an electrical engineer. I do image processing as a profession, and I wanted to learn how these things actually all work. So this is a little program that I've written actually in MATLAB, developed in the MATLAB app designer that I'm using for all my processing because I sort of want to, work out exactly how it works. And I decided to focus on just the narrowband, so I'm only processing the SHO, and I sort of focused on 2 regions separately. I primarily focused on the one region in red because there's so much structure in here. And if you look at the data, they sort of look like 2 sort of separate regions. So I just wanted to look at this one region, and it's 2000 by 2000 pixels. So the very first, you bring it in, and I did a very simple, linear stretch just to see what the data is. And so what I noticed very quickly was the hydrogen alpha and the O3 are actually very similar in sort of their structure and the characteristics. And the sulfur was actually slightly different. It has, definitely highlights different parts of the nebula. So, that was the first thing I noticed. And the next step I did was a very simple HDR, which is a global nonlinear intensity remapping. There's the algorithm called a Reinhard. And so this, now brought out, we can now see sort of like the background structures and the foreground structures. And so this was the very first, the first operation I did. And then I just combined it. This is, there are multiple steps on here, but this is just to take you how I did it. So this is the SHO to RGB, and then I just bumped up the saturation with a gamma of 2 to try and improve the colors, get some more color coming in there. So that was the first step, and that looks good, but it looks a little green, and and the stars look a little, they sort of have red halos around them. So that was just the first step. The second step is I applied blind deconvolution. This is actually part of what I did my PhD research in, was blind deconvolution. So I sort of that's my one hammer, and I throw everything at it. You might be able to see the images blinking. This is, I'm just blinking between the original and the deconvolved. I applied a wavelet noise reduction to the data first, then applied the blind deconvolution, which basically I just gave it an area of the image and say, work out the point spread function from this data. And then I applied that to the entire image. And, there's not a dramatic increase, but the stars definitely tighten up. And I actually find that the process of this sort of enhancement, which is improves the contrast and the resolution without increasing the noise, actually has a lot of benefits later on in the processing. So I find that the future processing comes out much better if you happen to deconvolve it at the start, even if the deconvolution doesn't seem to dramatically improve things. So these are the blindly deconvolved regions with that same HDR processing, and we're starting to see some good contrast and good structures and features coming out. So, and then I applied contrast limited adaptive histogram equalization. And this is a standard function that's available in MATLAB, and I'm assuming it's available in just about every standard image processing package. And the thing here is hydrogen alpha and oxygen 3 processed very similarly. The sulfur, I slightly tweaked the parameters just to make sure that the output histogram for the sulfur will look very similar to the hydrogen and the O3. And so now just combining these narrowband channels. So this is LRGB, which is, I use the hydrogen alpha as my luminance, and the SHO for RGB. And again, very simple saturation and luminance increase to sort of improve the colors and bring out a bit more of the data. And again, looking a little bit green for my liking. And so this is where the part where, I don't know if anybody does this. This is just my way. I've been, playing with data and just trying to work out how I see all these great images everybody produces with these beautiful, blues and golds and oranges. And I was trying to work out how everyone gets that. So I came up with a slightly different color palette. And this is what I call the ROC, or the red, orange, cyan color palette. And this may be what everybody does. But this is just to explain how I did it. So as we know, sulfur and hydrogen have almost identical wavelengths in terms of they look basically red. And the oxygen 3 at 501 nanometers is actually pretty green. But we know the Hubble palette goes sulfur is red, hydrogen is green, and oxygen is blue. And so that's the standard 3x3 color palette where you assign one color to one wavelength. What I've done is I've made the sulfur red, I make the hydrogen alpha orange, and then I make the oxygen 3 cyan. And I combine them in such a way basically you make your little 3x3 matrix. You work out how much of each, primary color is so sulfur is 1 red, hydrogen alpha is 1 red, half a green, and oxygen 3 is 1 green, 1 blue. And then you sum down the columns to work out how to scale them. So the red is now sulfur plus hydrogen. Screen. Sulfur plus hydrogen divided by 2. The green is half a hydrogen plus an oxygen divided by 1.5, and then the blue is just the oxygen. And the reason with the I don't do a maximum or something different is because if something is white, equal amounts red, green, and blue, this will still give white as an output. And after doing that, so this is now my color remapping. So those are the primary channels. And then this is now the, again, hydrogen alpha for luminance, and then SHO is now mapped to ROC, so red, orange, cyan. And then I simply boost the luminance and the saturation on a global level, and that's my my final image, which gives lots of really interesting details, and the sort of helps to bring out the browny goldy colors. The stars still look nice and small and pinpoint, and they don't seem to have magenta halos around them. And then at the end, simply all I did is I applied exactly the same processing to that other region, which was on the other side of the nebula. So that is my that was my very simple processing technique. It was like really interesting data to work with because it's not something I've collected myself. And yeah, the processing at the end looks very simple and straightforward. I definitely spent a lot of time like trying different things out, and some very subtle changes in how you handle the HDR or the contrast can give you like quite different results in terms of the what structures you're highlighting. You can make it more browny. We can make it more of the oxygen 3, but I'm now sort of inspired by looking at the other people to actually process the whole image as one and see what that comes out as. But anyway, that's my results. If anyone has any questions, let me know.
Rory, you want to take it?
Yeah, just want to say thanks for sharing that, David. And I liked your image because it was a portion of the data as opposed to the whole image. So that was something that was different too. No one submitted just a section of the data. So just wanted to thank everyone for sharing tonight. And let me give it one more take at sharing my screen. I just want to see if I could share some other images that were submitted by some other folks here. Looks like you guys can see that now. Is that right?
Yeah.
Yes.
You got a great big thank you, Jeff Duttons. There we go.
Okay. You guys can still see it. Let me see. Give me 1 second. Sorry about that. Okay. You guys can see that okay, right?
Yeah, we're seeing the big blue nebula here.
Okay, so this one was submitted by Jeff Dutton, and some of these are a little lower resolution, so they may look a little bit blurry. Apologize about that. But yeah, great image by Jeff Dutton. Here we have one by Martin Jacobitz. You can tell all these images are completely different than one another. Like I was saying earlier, that's what made this project so unique, and there's just such a huge variety to choose from. Next, we have Brandon Nance. He was going to present tonight, but couldn't. But thanks for your submission, Brandon. Appreciate that. And then let me see if I can say this. Matt Guinot. He's from France, so that's my best shot at saying that name. Thanks, Matt, for your submission. He was also going to submit tonight, but then realized it was 3:30 in the morning. He thought it was 3:30 in the afternoon here. So he couldn't present tonight. But thanks for your submission, Matt. And I think one more here, John Favalesa. Hope I'm saying that right. Awesome image by John. Thanks for your submission, John. And thank you. That's all we have tonight. And thank you, Terry, for submitting that data. That was awesome data. I had actually tried to submit. I had tried to process that data on my own. I'm trying to find how to quit sharing here. Give me a second. And it was really hard to process that data. I did okay, but your guys' images were great. So thank you.
I have to agree. It is quite challenging. Anything in the LMC is a hard target. It's just so wacky, but it's kind of an interesting target because you can look up and actually see a galaxy without a telescope. I think the standout channel is probably the S2. It has a lot of ridges. It's really, really strong. And as a standalone image, I think it looks pretty dramatic. If you blink between that and the HA, you can see the ridges changing. I tackled this image by initially combining the S2, the HA, and the O3, and the luminance with different weightings. Remember, I did this all in CCD stack at the time. I did different weightings with that because you need a place available when you add your color for the color to actually have an impact. That's why if you have HA and you throw color data, it looks pretty funky. So there was a lot of experimentation with the weightings until I had something I was happy with. Lately, I've been playing with this generalized histogram stretching, and that tool would make me tackle this image completely differently. But this is predates all of my pick stuff, so I was doing it the old-fashioned way, and I just really wanted to have a go at making an image using many filters. I do a lot of that with my stuff. I typically use narrowband and RGB together with most of my images. And I'd like to thank all of the presenters for coming on tonight. It was great. It's good to see that someone else is enjoying the data. I'll hand it back to you, Rory.
I'm going to take it over here. I think.
Okay, Alex. Yep.
I think I saw Rory say that's all I got, but his mic's not on. I want to go back. Conrad, how can we get access to this data? And I need to do something a little tricky here. My entire screen. Okay, this is our actual meeting room inside here. Now I'm presenting my screen, so I'm going to flip over to the TAIC workshop page, and that is on our website, theastroimagingchannel.org. And you see all these links across the top. One of them is TAIC workshop. You go to the TAIC workshop and you get a description of what a TAIC workshop is and the current workshop. The current workshop is Terry's data. Terry brings us the data for the Tarantula Nebula from his observatory in Australia. So you click this and you go get the zip file and you extract it all. And were this before March 13th, you would then go ahead and submit your finished image here. It goes over to a mail address that just hooks you up right there. Now, as I said earlier, there are other workshops that we have done that you can go back and you can get the information for those workshops, and you can also do them. They're just stacks of data that you can use to do however you want. So that should be answering your question, Conrad, about how you get the information. Here are the results from, I think it was Eric's data. Eric's M33. And here's all different, some of the people that turn stuff in, and you can see they're all different. It's always exciting to do this kind of a workshop. Not knowing how long we take today, I skipped my usual introduction. Starting next week, Drew Henry's going to be here for 2 weeks in a row to tell us about how he grabs his good solar system objects with his with his DOB. First week is going to be about how he grabs the data, and the second week he tells me is going to be about how he processes the data. So there'll be a lot of good things to do there. You can see that we have an advanced imaging conference no show, one of those days that we're taking off, and That's coming up the weekend before Memorial Day here in the United States, the weekend before the last Monday of May. And we're going to be gone, or many of us are going to be gone to probably probably the best imaging show you can get in the United States and maybe in the world. Ken Crawford's going to be here on April 10th. He's the organizer of that, and he's going to spend 5 minutes with us about what's happening at the Advanced Imaging Conference this year. So we are going to take a day off then, and Richard is going to be back. Why guiding needs to die, and how he's going to help make it happen. But then you can see that after that, we've got a lot of blanks. So go ahead, hit the contact button over here. Tell us that you want to be part of the Astro Imaging channel. It doesn't take all that much technical expertise to put on a show. Yeah, you got to be good. But we figure if you know how to push all those photons around and how to push these buttons on your Astro Imaging rig, you should be able to explain it to your buddies here in the Astro Imaging channel. So that's what's happening. Eric, how are we doing on any questions that came up while I was talking?
I think we're all good.
Yeah, I think we're all good. Okay, so that means it's time to say good night, everybody. I think I'm still sharing, aren't I? So I'm gonna take some time off here. I'm gonna stop sharing. I'm so glad you were able to come here with us tonight. And we'll see you next week when we go off to start taking images of the planets and stuff. So good night. Tim, thanks to Tim. He had to step in for Molly today. So Tim, thanks for all the streaming and all the backup work up here. Again, Jason, John, David, thank you for everything that you did tonight. Rory, thank you for putting it all together and organizing it. Thanks, everybody. We'll see you next week.